Welcome back to another episode of Organic Chemistry. I'm that chemist, and today we're going to talk about the synthesis of diazo compounds. But before we get into that, let's go through the practice problems that I assigned last lecture. So in this first reaction, we initially have a hydroboration reaction followed by treatment with base and peroxide. And so the goal of this question is to get you to figure out how this reaction occurs. So initially what happens is this 9-BBN, which is a borane, is able to do hydroboration across this alkene. We can then undergo an oxidative cleavage of this borane through a 1,2 shift with hydrogen peroxide, giving us this alcohol as our product. Now it's worth noticing that we're under basic conditions here in ethanol, so this alcohol can be easily deprotonated. Once this gets deprotonated, an intramolecular lactonization reaction can occur where the alcohol is eliminated as a product, shown here. And so we get this lactone as a side product. Now once we have this alcohol, this alpha hydroxy ketone, this is a ketol, and so this can undergo an alpha ketol rearrangement. And so what occurs is this alcohol is able to collapse down its electron density, and we have this cyclobutane rearranged to form a cyclopentane, giving us 2 cyclopentanes, while this other 6-membered ring is still retained. Now in this next problem, we have this methyl ether containing allene. And so if you recall from other vinyl ethers, it's possible to protonate them and convert them into the corresponding carbonyl. So initially, via protonation of this alpha position, we're able to open this up with water to give us this ketone, an alpha-beta unsaturated ketone, which does a similar alpha-ketol rearrangement to give us this cyclopentenone product. Now in this next problem, we have a Craigie rearrangement. And so what occurs is first we esterify this hydroperoxide, which can then undergo a not a sigmatropic rearrangement. This can undergo a 1,2 shift, so that this rearranges, giving us this oxygen bridge here between this big ring. What can then occur is hydrolysis of this ester under acidic conditions, followed by the rearrangement to afford this macrolactone. And then finally, we have this free hydroxy group, which can react with acetic acid under acid-catalyzed conditions to give us this acetate product. Now let's get to today's material, the synthesis of diazo compounds. So I know I'd promised that I was going to do Diels-Alder next, but because it was just such a long topic, I've actually delayed it. So today we're going to talk about diazo synthesis. So there's several different strategies that are possible. I have a review at the end of this slide, which will summarize some additional ones, but the main ones I'm going to list here. So the alpha diazotization of reactive methylene. So this would be like the alpha diazotization of ketones or esters. The treatment of ketones or aldehydes with hydrazine so that you synthesize a hydrazone. It's also possible to use Tosyl hydrazine, which is the main thing you see in the literature. Additionally, it's possible to take the amino group of an amino acid and diazotize it. There's also the acylation of diazo compounds, which we briefly discussed, although we were mostly looking at them as intermediates in episode 46 and 47, which I'll put a card to here and here, respectively. And it's also possible to do transition metal cross-coupling. But because we haven't touched transition metal cross-coupling yet, because it kind of makes all of our syntheses a lot easier, we're going to hold off on talking about that for the time being. So I'm not discussing this. So this really great review here kind of has the best summary of all the different methods of diazo synthesis. And so if you're curious about this, I'll include the link to this in the description. So Diazo-Transfer Reagents. These are probably the most common way to synthesize diazo groups in the modern day and age. And so the main ones would be like Tosyl azide, the para-acetamide analog of Tosyl azide, and there's many other sulfonyl azide containing Diazo-Transfer Reagents. There's also some other ones such as ADT, which kind of looks like melamine. There's just certain types of azides that are really good at this transformation. But overwhelmingly, Tosyl azide is the most used, although you will see other ones used occasionally. So imidazole sulfonyl azides are reported to be somewhat more stable, although this is controversial because some people have had instances where detonations have occurred while others haven't. So I'm not going to focus on those too much other than just to make note that those might be desirable. It's also, they can be protonated, so that's kind of useful for removal as well as their isolation. Okay, so I'm going to add in this mechanism into this next slide. So here you can see that with this electron withdrawing group, which could be a ketone, it could be some other sort of carbonyl, such as an ester, an amide, or something like a nitrile, it's possible to deprotonate this alpha position using something like DBU. Sometimes stronger bases are required, but in most instances, DBU or triethylamine might be sufficient. So here we can see that we have our sulfonyl azide, and this negative charge in the alpha position is able to attack. This is then able to migrate some electron density from the triple bond onto this central nitrogen, which gives us this diazo species, which can then have another deprotonation occur, allowing C double bond N to form, and allowing this sulfonyl with the nitrogen to leave as a sulfonamide. Just through some proton transfers, this eventually goes to an NH2. Here, this is deprotonated, but this could easily be protonated by the solution or via the original, base-mediated deprotonation of the starting material, giving us this final diazo compound. Now, the conditions that you use for these have to be a little bit careful because those diazo groups can usually be easily substituted. These ones are a little bit more stable than like unactivated ones. Because these aren't synthesized through a diazonium intermediate, they're just directly to the diazo, they're a little bit easier to work with. So a common example would be something like this, where we have phenyl ethyl acetate, or in this case, phenyl methyl acetate. And so this acetate group, this phenyl acetate group, is able to be diazotized in the benzylic position. It's also further made basic, or rather acidic, due to the presence of this electron withdrawing group and the benzene. So this can easily be diazotized. I've done this type of transformation on substrates before, and it works great. So another example is the treatment of Meldrum's acid with this 4-acetamido version of the sulfonyl azide with triethylamine, and this is able to be cleanly converted in 30 minutes. Now, some more pharmaceutically relevant examples include the treatment of this ketoamide derivative with mesyl azide. This is just a mesylate version. Instead of Tosyl, they have a mesyl. And with DBU, this is cleanly converted in 4 hours at room temp in the presence of a TBS group as well as a trityl-protected nitrogen. It's also worth noting that this is a Weinreb amide, so they're probably planning to add in a Grignard later on. Now here we have an interesting example where we have both a nitrile and a ketone, but sodium hydride is used. And so this is obtained in 69% yield. Now the next approach that you could take is the treatment of a hydrazone with an oxidant. So if this is just a normal hydrazone, you have to convert this to the N2 derivative. If you have the Tosyl derivative, you can more easily form the product just under basic conditions, but here an oxidant has to be used. Typically this would be manganese dioxide, although Swern oxidation conditions typically work for this as well. And I'll include one example later on where we can see a copper catalyst used in the presence of oxygen as an alternative way to oxidize this. So the Tosyl hydrazone method is a little bit better. Depending on how stubborn this is, you might need to do like a destructive distillation. So just like pyrolyze it and collect it on a cold finger kind of thing. And I've had to do that before for the diphenyl diazomethane. But in this case, it can be done under other conditions as well. Usually like a milder base is fine. However, depending on what happens to the sulfonate, if you just want to get rid of this, you can distill off the product if you do that under really low pressure. So you can see just a deprotonation occurs, then a shift of the lone pair on the nitrogen to the terminal nitrogen is able to displace the sulfonate as a leaving group, giving us our diazo compound as our product. So some examples of this include the treatment of this dioxyindole derivative, which is called an isatin. You can see that the ketone of the isatin has just condensed with tosyl hydrazine to give us this tosyl hydrazone. Sodium hydroxide in water at 50 degrees Celsius for 3 hours was enough to convert this to the diazo. Now in this next example, you can see this interesting 2-pyridine containing system. This is cleanly converted to the diazo as well. Now in this next case, we can see that if we have a normal hydrazone, we have to use an oxidant. So here's an example with manganese dioxide, where this product was obtained in 87% yield. So in this next example, we can see the example I was talking about using copper and oxygen just from the air. They also use silica gel, pyridine, and water to accomplish this transformation. But you can see that this trichloroethyl group was well tolerated under these conditions, affording the diazo in 94% yield, which is quite good. So the next method I'm going to talk about is the diazotization of amino groups. Now, while I originally mentioned that this could be done on amino acids, this could be done on other groups with amino groups. It's just most commonly seen when you have an alpha carbonyl to the amino group. And so if you use nitrous acid, one thing that's worth considering is because this is forming a diazonium first, if you use something like HCl or HBr, you're going to get the chloride or the bromide corresponding to where this amino group was. So you have to choose your acid carefully if you're going to use nitrous acid. However, most of the time in the literature, you'll see nitrites used for this reason. So here you can see the mechanism of this reaction is the amino group is able to attack the nitrite. This just displaces the alcohol's leaving group. This diazo hydroxy compound is able to form a diazonium through elimination of the hydroxide as water, giving us a diazonium salt. Now we have an alpha proton that could be deprotonated from this carbonyl. That then just gives us our diazo compound as our final product. So some examples of this include the treatment of this penicillin derivative. You can see that this amino group is cleanly converted to this diazo. And in this other example, we can see we have a pyridine with some halogens and an amide. This is well tolerated, and the corresponding NH2 group is converted to the diazo, although no yields were given in this paper. In this next example, we can see that we can have an alpha CF2 as well as a phosphonate as our electron withdrawing group, and this is able to be quantitatively converted using tert butyl nitrite. And in this paper, they just used these as an intermediate and then underwent 3+2 cycloadditions to get their products. In this paper, you can see that they take this quite complex heterocycle-containing derivative, and they are able to cleanly convert this to the corresponding diazo in 60% yield. And so you can see that a lot of functional groups are tolerated, which might be somewhat surprising. So for this lecture, I'd like to assign 3 practice problems. In this first problem, show how you could go through this entire sequence of steps, and you just need to propose conditions at each stage. So how are you going to convert this styrene to this epoxide? What would you use? And so you just do this for each step. Now in this next question, I want you to show how you'd convert this alcohol first to this ethyl ester, and finally how you'd synthesize a diazo compound from that. So this should test the diazo synthesis that we discussed today quite well. And in this final problem, I'd like you to show how some starting material could be treated with an organic nitrite to give us this diazo compound shown here. This should be relatively straightforward. So hopefully you've enjoyed this lecture. If you have any questions or comments, I'd encourage you to leave them below. And if you haven't noticed, I set up a Patreon, and if you're interested in helping out the channel, that would be great. If you're a high school student or an undergrad, I don't expect you to contribute at all. But if you have a job and you're making money and you feel generous and you're willing to help out, I would really appreciate it. Have a great day.